Hello, I'm Steve Ritchie and I'm going to introduce you to Delith. Delith is a twin Vortex turbine produced by Gilkes. We think she was installed around about 1920 here, but think she was a second-hand turbine bought in. They had an earlier one, which is in the Gilkes order books, and implies that she was probably one of the very first twin Vortex turbines that Gilkes produced. It was on its way, as this design developed, to becoming an early version of a modern-day Francis turbine. And we've got a few modern additions. One of them is this control panel. So I'm just going to start the turbine up. It's just going through some initial checks now. It's enabling generator. That's all okay. It's taking up to 50 RPM. Just checking that that's all okay. And it's doing a torque check. So basically it's opening up the vanes. So these black veins in here, you'll see starting to gradually open up, let the water into the turbine. The rotor is now producing a torque onto the belt drive. See, we're up at, what are we now, 8 Newton meters. It's got to get above 10. And then once it sees that torque, it knows that the belt drive here, which is inside the black casing, it's a 3.5 to 1 ratio, speeding up the rotor speed to the generator speed, so we're operating at optimum efficiency with the generator. The power check, it's got to get above a kilowatt. So now you can see the vanes have started to open up quite noticeably. What we got up on the right hand side here is the intake, so we've got a screen, the grey line coming down. We've got the lake side on this side, and we've got inside the screen on this side. The screen starts to get blocked, this level will start to go down while the lake stays constant. It sends out email warnings to say the screen is blocked. If it then gets critical, it starts to really try and suck things in through the screen. It will shut down before it sucks in anything significant. That's to stop the screen getting really clogged up. When it does stop, as long as it hasn't been sucked in, the material on this side of the screen will just fall off. Here's the old hand wheel they used to use to open up the turbine, but we have now added on at this end an actuator. So what we have is a DC motor driving 100 to 1 planetary gear, which is then driving a 10 to 1 worm gear in the gearbox. Overall we've got an 800 to 1 gearbox ratio. And the bit sticking out the end here is an absolute encoder, just so we know exactly what position the rotor is. And we see that then turns another worm, which turns this big wheel down below. And going round to the other side, that shaft comes out the other side on the hand side, and this linkage system then forces all the vanes to open up together in parallel. And you can see that external linkage here on the diagram. We've got a modern Synchronous reluctance generator. That's about 94% efficient, that generator. It's a full variable speed machine, and the electronics that control it is all in this left-hand control cabinet. It's driving the magnetic fields here at a control speed of around about a megahertz, 1 million times a second, which allows a very accurate speed and torque control of this generator. And for this kind of machine where we were having to do paper calculations about what the speed was, it was really important for us to be able to vary that speed and find out where its optimum performance point was. And we can see here on this time trace, if I just scroll back in time, there's where I opened it up for a demo earlier on in the day. We had quite a big rainfall this morning, and you can see the lake level and the screen level rose up as more water flowed into the lake, which I'll take to see in a minute. Now you see it's now opening up to maximum. That's because the lake level is above 74 centimetres, loads of water in the lake. We just want to dump as much water through the turbine as we possibly can, otherwise it just spills out of the lake and is wasted in terms of power. It's a twin vortex because the water exits from the rotor on both sides. It comes out from the centre of the rotor into these draft tubes, one on this side and one on this side. They dip down into a sump below here where the water level is about 1.5 meters down. Now as this thing gets up to speed, what's happening is all the air has been evacuated from these tubes, and the water column lifts all the way up right back, so there's no air actually inside the turbine. And then we've got 1.5 meters of water column sucking at the water out of the turbine. And we've got 12.5 meters head above the inlet. So in total, we've got 14 meters of head across the turbine. So it's making best use of the head. This is where I spend a lot of my time coding up the PLC, which is now finished. Off we go. Let's click the rake. Building's locked up. And we're gonna just follow the penstock route up. So I'm gonna jump over this fence into this field of gunnerer. Now walking on top of it. And then it crosses a stream over here. So we had the pipe cleaners down here. This is the original cast iron pipe. And so they jetted up from here and they used the water pressure close to the yield pressure of steel. I'm just going to walk my way along here. Right, I've done the most dangerous bit of the video. So now goes underground again. So this is basically what we're seeing here is a spillway from the lake. And the pipe is all going underground from here. And actually goes underneath the ground through these trees. So the big advantage of doing the pipe cleaning was that we didn't have to dig up through some really beautiful grounds at Margam Country Park. Just up this path here in a minute. There she goes. There's Margam Castle, built by the Talbots, who were the people who put in the turbine. And that turbine used to power the lights in the castle. I was saying before, they had a smaller turbine in originally, and the intake for that turbine was quite a long way up the valley. It was a run of river, so when there was water in the river they could power their lights. When there wasn't water in the river they couldn't. They obviously liked their electric lights, so we decided to build a lake further down the catchment so we could get the storage, and they could then store up the water and just run the turbine at night. Right, and here we go. Here's what I call the storage lake, other people call the fish pond. Now, what we did was we had to put this all in new. Originally, the lake came up to this line of wood here, and the intake chamber was underneath this grass. That all got filled in, clay was packed in, pipe was sealed up with a concrete plug. So it's quite a major exercise to dig from here and then install all of this lot. And then under here is the screen. So you see that's going at full rate, well oversized the screen so it doesn't get blocked up. Right, now we have complete length. I'm trying to do this one-handed. Out of sight, keeps on going, and there we go, we're down at the bottom. Close the top. And there you have it. One hydro scheme finished.